everyone. In the previous class, we discussed about Ladanyi's rock mass tunnel support interaction analysis, which is an elasto-plastic analysis. And there we learnt about the analysis of stresses as well as the deformation, and using this information we were in a position to draw the ground response curve. What about the support reaction curve and the analysis of the available support system? So, we will take a look at some of these aspects today. So, just to give you the idea what this analysis was all about. So, we had the circular opening with the radius Ri. It was subjected to the internal support pressure as Pi. Any point in the rock mass was designated by r comma theta, where theta was the angle measured in the anti-clockwise direction from the horizontal axis. Then you had the elastic plastic boundary, beyond which the rock was the intact rock and it was behaving as the elastic one. And in between the boundary and the tunnel periphery, we had the broken zone, which we consider to be acting as the plastic zone. It was assumed that this complete system is acted upon by the hydrostatic state of stress represented by the stress P naught. Then when we were discussing about the analysis of deformation, we saw this particular figure where if you just take a look, RO is equal to Ri plus Ui. Ui was the radial displacement of the tunnel periphery, and similarly as far as the elastoplastic boundary is concerned, we have REO is equal to Re plus Ue. So, this is how we carried out the analysis of deformation. Now, today we will focus on the support systems. So, what is going to be the equation for the required support line? So, here for Pi critical less than Pi less than P naught, the response of rock mass is elastic. We have seen this in the previous class, and the equation for required support line will be given by the equation Ui upon Rio is equal to 1 plus mu upon E into Po minus Pi. You take a look at equation number 14 of our earlier class, and then you will be able to get that from where this equation is coming. So, we will write this equation as equation number 25. So, since we are doing this complete derivation of Ladanyi's elastoplastic analysis of tunnels for the last couple of lectures, so this is all in continuation. Now, here this Pi to vary from P naught to Pi critical. So, this what we will do is, after I explain you this analysis, we will take up an example with the help of Excel. We will try to solve it, and there you will realize that how do we vary this Pi and how do we carry out various steps in the analysis. Then we have the equation for Pi less than Pi critical. The plastic deformations are going to be there in this case. and these are represented by equation number 18. So let us see that how the required support lines for the rock surrounding the tunnel looks like. So on the x-axis we plot this ui, and on y-axis we have this radial support pressure, which is pi. So we need to draw this. So the top one is for roof and the bottom one is for the floor, and the middle one is for the side walls. And then these two distances, they are gamma r into Re minus Ri, each of these, where you have this gamma r as the unit weight of the broken rock. So this is what is the required support lines for rock surrounding the tunnel. So if you recall our discussion, I mentioned to you that there is going to be the broken zone in the vicinity of the excavation, and they will exert an extra weight on the roof of the tunnel. That is why what we did, that we considered the analysis of the tunnel without this additional weight, and then I mentioned to you that we will take care of this weight after the analysis is complete. So this is how that we are going to do this. That is the required support line, which are defined by equations 18 and 25. These can be considered to represent the behavior of side wall of the tunnel, because the stresses and deformation in the side walls, they are not really influenced significantly by the dead weight of the broken zone surrounding the tunnel. But what happens at the roof and the floor of the tunnel? Yes, that weight of the broken zone, broken rock is extremely important. So in order to allow for the dead weight of broken rock in the roof and in the floor of the tunnel, what we need to do is we need to increase or reduce the support pressure Pi. So it is increased in case of roof and it is reduced in case of the floor of the tunnel. And what will be the amount by which it should be increased or reduced? It will be gamma r into Re minus Ri, where Re and Ri I just showed you with the help of a figure. Now we need to take a note here that this correction can only be done after we have got the required support line for the weightless condition, which we can get from equations 18 and equations 25 for elastic and the plastic zones respectively. So this is how the support pressures for the roof and the floor they can be obtained, because in case of the side wall, whatever that you get, you need to add gamma r Re minus Ri, and then you will be getting it for roof. If you subtract, you will be getting for the floor. Now coming to the analysis of the available support, basically these support systems are usually installed after a certain amount of convergence has already taken place in the tunnel. Why this is so? We have discussed already that in case if upon the excavation you don't want to allow little bit of the deformation, then you have to go for very rigid or stiff support system, which may be quite uneconomical. Therefore, usually certain amount of convergence is allowed before the installation of the support system. This initial convergence which I am denoting by maybe UIO, this will be UI equal to UIO plus UIE. Give me a moment and I will explain you how this is going to be done. So let me draw a figure. So on the x-axis I have UI and here I have PI, and see here this initial convergence is allowed, which is say UIO, and then we have some stiffness of the support system, and after that it becomes like this, horizontal. So this we are calling as PS max, and if you take any point corresponding to which you will get one value of UI and here you will get the corresponding value of PI. So basically the elastic part of the total deformation is UIE. So here if I want to show it in this figure, so basically it will be this distance that is going to be given by UIE, and of course its slope will be K, which is the stiffness of the support system. So basically what I have drawn here is the available support curve. So here this Px max is the maximum load carrying capacity of the support system or you can say that this is the strength of the support system. Now the question comes that what is the stiffness of the support system, which is K. So the stiffness of the support that is installed within the tunnel is characterized by the stiffness constant, which is represented by K. So the radial support pressure Pi, which is provided by the support, can be given by Pi as K into UIE divided by Ri. I will mark this as equation number 2, and what we will get from here is UIE divided by Ri is equal to Pi upon K. So here this UIE, as I mentioned, it is the elastic part of the total deformation, which is UI. So from this equation number 1 that I gave you, that was ui equal to uio plus uie. This is what that we had. So this we can write as uio plus pi into ri upon k. If I just substitute the expression from equation number 2. So this is what that we are going to get as equation number 3, or we can also write it as ui upon ri is equal to uio upon rio plus pi upon k. This is equation number 4. So basically this k here is in kilonewton per meter square, and you have this ps max and k as the function of nature of the support system, its geometry, and the mechanical property. Now take a look at this particular figure where this ui is represented on the x-axis and pi is represented on the y-axis. We have a value of pi critical. So here what we get is the first curve, that is roof, which is represented by green color curve here. Then we get the side wall, and the last one is for floor or invert. So you see that here corresponding to for example say floor. So what you will get here is as ui invert. Okay, and for this one roof you will have this as ui as roof, and this red one will be ui of the side wall. So basically these three, ui invert, ui roof and ui side walls, these are the equilibrium deformations. And corresponding to each of these, we have here pi invert, then we have pi side walls, this one red one, and the green one is pi roof. So these three are the equilibrium pressures. And here this is what is ps max. So basically this portion is going to be the plastic deformation of the rock mass support system in roof. So this is how first we draw the GRC for roof, side wall and floor or invert from the analysis that we learnt in the previous class, and this is how we can get the support reaction curve for any kind of support which is available to that particular system. The question comes here that how to determine this stiffness. So all the different types of the support systems such as shotcrete, steel sets, rock bolts, you have the separate expression for this stiffness that we will see in a short while. So therefore if we want to draw now, let us say both together, that is GRC as well as the support reaction curve, this is how it is going to look like. This is what is UI, and here PI, and beginning I have P naught. And let me draw just one ground response curve. And the initial deformation which is allowed is say UIO. And then from here, let me draw and explain you how the different types of the support systems, they will have their support reaction curve. So this is the first one, second, third, and the fourth one. So corresponding to the first one, let us focus first. Say that it has the stiffness as Ks1. Similarly, the second one has Ks2, the third one is Ks3, and the fourth one is Ks4. So here this UIO is this distance. Now corresponding to this, the first one, here you will get a value of UIE. Similarly, for the second one, it will be more, the deformations are going to be more as the stiffness of the support system, it reduces. So the first one we can write as very rigid support system. You can see that the total deformation is only this. Now we change the stiffness of the support system from Ks1 to Ks2, and the resulting support reaction curve corresponds to this situation too. So here, although it is more than the case 1, but still it is not that large as compared to case 3 and case 4. So maybe we can write it as the rigid support system. Coming to the third one, when we go from Ks2 to Ks3, that means stiffness is further reduced. So in this case, maybe we can recall this as the flexible support system. And in case we further reduce it to Ks4, what we have is very flexible support system. So you see, you go for more rigid support system, the resulting deformations are low. In all the 4 cases, we have made the tunnel to experience the initial convergence of the magnitude of UIO. Now an example of these different types of support systems may be, let us say, just for an example corresponding to one, let us say that maybe it is ISHB 450 at the rate 1 meter center to center, and then maybe 4 we can say that it is ISMB 150 at the rate 400 millimeter center to center. So depending upon what type of the support system it is, we can choose the appropriate cross section corresponding to different types of steel sets. So it is not only the steel set that we can have, you can get different thickness of the shotcrete or maybe different types of the rock bolts. So, the point I want to make here is that the moment you start reducing the stiffness, the resulting deformations are going to be larger as compared to a support system which is stiffer in nature. So, this is how we can obtain or we can draw the combined ground response curve and the support reaction curve. The question still remains unanswered, that is how to determine the stiffness of the support system. So, we will try to explore this question's answer in the next class with the help of the support systems such as shotcrete and the steel sets. Thank you very much.